Okay, to explain Newton's third law, which everyone at least is familiar with, for every action there's an equal and opposite reaction. I usually illustrate it by punching walls, but my camera is too far away from a wall, so well, I'm going to substitute the wall with, I'm going to punch a book. And the book, to be honest with you, has had it coming for quite a while. So let me punch this book. Great. How do I know I punched the book? Well, because my fingers kind of hurt there. My fingers don't normally hurt, but all of a sudden I came into contact with this book and all of a sudden my hand hurt. Turns out I can't hit the book without the book hitting me back. And in fact, when I punch harder, it hurts more, right? Well, why is that? Because I exerted more force on the book exerted more force on me. For every action, there is an equal and opposite reaction. It's equal in magnitude and opposite in direction. I hit the book in this direction, the book hits me in this direction, causing my hand to stop and also causing my hand to hurt. Now, where you have to be careful is in applying this. So, for example, let's imagine I've got a crate. I'm going to illustrate this here on your screen. So I've got a crate that's on a floor somewhere. I'll make my floor. And I've got a guy pushing on the cart, or on the crate. He's got really long arms. And he's really pushing, he's really digging in there. So let us examine the forces acting on the crate. Okay, so I'm actually going to make my little dashed line. And let's say that the crate's moving along, sliding along the floor at a constant velocity, for example. So I'm going to do a force diagram. Now let me just go through all the forces acting on the crate. Well, first of all, the Earth is pulling on the crate, so we have a weight downward, W. The crate is neither flying off the surface nor crashing down into the surface, and so there is a support force of the floor acting upward on the crate, which I think we typically have done in kind of a light blue. So I'm going to put a little normal force here. Notice again, I drew it to be the same length as my weight. Why is that? Because I don't want to have any net force vertically, because net force, a non-zero net force would indicate acceleration, and I don't have acceleration vertically. Now how about horizontally? What's going on? Well, the dude is pushing the crate, correct? So I need to put a push force, and I'll put it right here. Force of push. And let's see, just like I can't punch the book without the book punching me, doesn't the crate push on the guy? I know his fingers, when he's pushing on the crate, don't they get smashed in a little bit? But you have to ask yourself, while that is very true, that is a very valid force, I wouldn't draw it in my force diagram. Why not? Because the force of the crate pushing on the dude is a force on the dude, right? Be careful to identify the object upon which the force acts and ask yourself, is that the object that I'm really caring about? We don't care about the dude. We care about the crate. So yes, we do include the force of the dude pushing on the crate because the crate is the object of that force. The crate pushes on the dude, but we don't care about that force because it's on the dude. And we're not concerned right now about the forces on the dude. We want to know, why is this crate moving the way it is? So we need to isolate all the forces acting on the crate. I left one out, didn't I? What's the other force? Well, gosh, let's see. This crate is sliding. It's sliding along the floor. Remember, those little nooks and crannies are sliding along the floor. The crate is pushing on the floor forward in a direction to the right, correct? But we don't care about the force of the crate on the ground or on the floor. We do care about the force of the ground on the crate, which is to the left. So we need to include a force of friction. I'll do it in purple. Of the ground on the crate to the left, opposing his motion. So sure enough, I have now listed all the different forces acting on this crate, and it turns out both vertically and horizontally they're in balance, which means I have no acceleration in either direction. In the case of vertically, I have no motion. Horizontally, the thing is in motion. It's moving, but it's not speeding up or slowing down. It's moving along at a constant velocity, and you should know by now that constant velocity means no acceleration.